Hi, welcome. In this video I'm going to work with a technology I've never worked before, and it is this right here. This thing here is magnetic bubble memory. Now we're going to work on this with the Heathkit H8. I've been doing a lot of videos on the H8 lately because it's a great platform for building moderately sized expansion cards, and there's a lot of existing expansion cards out there, plus a few that I've designed myself. Now my go-to board so far for storage on this has been this board here, which is designed by Richard Davis and Norberto Collado. It is a dual compact flash board, so you can see your two compact flash there. These things appear to the H8 as hard drives. It's a great board. You could probably store every piece of software that's ever been written for the H8 on that board. But what I wanted to do is I wanted to experiment with technology I've never done before called magnetic bubble memory. And that led to this board here. Now magnetic bubble memory, I believe it was invented in maybe the 60s and maybe had its lifetime through the 70s and maybe even into the early 80s. It was kind of pushed out by newer, denser, cheaper, faster technologies. But for a while this was what you would use if you wanted a non-volatile memory-based storage device. There's no moving parts in it. It uses magnetic fields, and it's really a very interesting technology. So this board here uses a 1 megabit Intel 7110AZ bubble memory IC, and 1 megabit gives you about 128 kilobytes of memory, which is about on par with the 100 kilobyte H17 floppies that would have originally gone with this computer. So it's a good fit for the H8 computer. Now, why would someone choose to use bubble memory over some of the other storage technologies at the time, like say floppy drive? Well, floppy drive has moving parts. You know, you've got a spinning disk, you've got a moving head. That involves, first and foremost, you've got seek time, latency to get to the track and the sectors you want to read. But it's also a moving device that is subject to vibration and just durability over time because of all those moving parts. So just like how we like SD cards and other solid-state devices now, these bubble memories, they were nice because they had no moving motors, no platters. You could put them in a high vibration environment like a piece of industrial equipment, and you know, they would survive just fine there. And I think that is where these things really found a niche. Even when newer technology came along, these things still lived in sort of the industrial space for a little while. So I'm going to build up this board and I'm going to put together a storage driver for it so that we can use it as a storage device on the H8, and then we will actually boot off of it and run a basic program or something from it.
Okay, when getting started in bubble memory, I looked up a bunch of resources online, find what I could. There was not a lot, but there's also a little bit more than I expected. So the first thing, of course, is the Wikipedia page on bubble memory, and you'll learn that it comes down to someone named Andrew Bobeck, who was one of the earlier developers of bubble memory. He was with Bell Labs back in the 60s, 70s, and working on something called Twister. And it'll describe how Twister led to bubble memory and led to kind of this thing with these T's and these bars and these coils that go around it and will cause bubbles to move around the substrate. It doesn't go into a lot of detail in this relatively short Wikipedia article, but there are better resources out there. And then the next resource is this video here. This is an AT&T video from 1979, and this is an interview. I believe it's with Bobeck talking about bubble memory. They talk a little bit about how it works. It's only like 6 minutes long, but it's interesting historical perspective. Doesn't really give you enough detail to understand it, but gives you a little bit of a detail to see what they thought the promise of this was. Then we get into Craig Andrews' web pages. So Craig Andrews, he developed this SBC85 retro computer project, and he made a bubble memory board for it. And I found this to be indispensable. And it's actually Craig who sold the initial kits that I was able to get started in bubble memory development. And Craig was helpful answering a number of my questions. But, you know, you can look at his board and there's actually, you know, he's got blog posts on it. He's got documentation. Let's see, can we click through this? Documentation on you see, he's got a number of different boards, but there's the bubble board, and bill of materials, user's guide, schematic, data sheets, all kinds of stuff if you wanted to build one of this for his SBC 85. And Craig has also produced a series of videos. One of them here, he goes pencil and paper and shows how the magnetic loops work and how the bubbles go around. Another one, he's showing how the T's and the bars work to move bubbles around using Skittles. This illustrates it really well. Another one, he's got Keurig pods, and he's showing how magnetic domains work. And here, he's got one of the bubble memory modules torn apart. So I'm not going to go through all of the theory of bubble memory because it's already been done with this series of videos right here. And if you want to go watch all these, you will learn a lot about how bubble memory works, how the devices work. I'm going to concentrate more on the practical application of getting it to work on my Heathkit H8. One other thing I had here was this video I found, Digital Electronics 25, and it's got some really cool visualizations. Like if I click this one, you can see all of the bubbles moving around on the T's and the bars. I'm not going to talk about the T's and the bars, or in the newer memories, it'd be the chevrons. That's more of an implementation detail. You can watch Craig's videos and learn about how the actual bubbles move around on the substrate. Like I say, I'm going to mostly think about the practical implications. So.
Okay, we're going to attempt to visualize the magnetic bubble memory using my daughter's marble run. So basically, there's a high-level visualization, there's a low-level visualization. The low-level visualization would be very close to the actual hardware and would have little T's and bars or chevrons, and you would see the bubbles move based on the fields on those T's and bars. This higher-level view is kind of a loop view, so you're taking kind of the next level of abstraction up. Visualize what's going on inside of this module, and this is like one of these modules here, like this MTech one or this Intel one. So what it has is it has a loop, and there are bubbles, magnetic bubbles on the loop, and they go round and round. So I can push them like these marbles, and they're just going round and round. I'm not creating any of them, I'm not destroying any of them. They're just kind of going around on their merry way. Now, in order to make them go around, it uses some magnetic fields at 90-degree offset. So it has a set of coils wrapped around one way, a set of coils wrapped around the other way, and it puts power into those coils to generate magnetic field. So your magnetic field is alternating. Each time you alternate the field, it will step one bubble. So you alternate your field once, you get the next bubble lined up here. You alternate again, you get the next one. So and so like that. 4,096 times around to do the whole loop. Now you've got 272 of these loops connected together via a channel at each end. And the reason it's 272 is because this thing does 256 bits plus 14 bits of error correction, and they kind of rounded it up to 16. You get 272. You can configure the module in two different ways to either use those additional 16 bits for yourself or leave them as ECC. If you use them for yourself, you end up with these very oddball sector sizes that don't divide evenly, because 272 is not a power 2, whereas 256 is. So in my prototype, I'm going to use 256. So imagine 256 of these in parallel. Now, just moving the bubbles around in a circle, we're not, we're not getting any data on or off of it. We're just taking the data that's there and moving it around. So how do we get data off of it? Well, what we're going to do is we're going to apply the magnetic field. We're going to take all 272 of these. Whoops. You get up there, join your friends. And we're going to advance it to the one we want. Like, let's say we want this orange and red one. And what we will do then is we will replicate that bit. So we've got a replicator here. It replicated it right there. Now, I wish I had another orange and red one to, complete the visualization, but I don't. I have these slightly smaller blue marbles. So it replicated it, and then it puts that replicated bit out here on the line. Now, all 272 other ones of these put their bits out here on the line, and we have a 272-bit line. And that is how we will read. Then we'll just take and run them all out, and they can all go out to the detector. All of them shoveled out. Then if we wanted to read the next sector, we would move all 272 of these up to the next bit. We'll duplicate that bubble because we don't want to destroy that bubble. We'll duplicate it, and we will move it to the output line. And his 271 friends also moving their bubbles to the output line, and kick them out there to a detector where we can read it. So we can do that. We can read all 496 bits, or all 496 bubbles at 272 times. You'd read the entire megabit of memory if you did all of that. And we never destroyed any of these bubbles when we were doing that because we duplicated them down there at that end. Now if we want to do a write, the process is very similar. In that case, we will put the bits we want to write down here in this line, all 272 bits, line them up there so each one of these cells would have the bit we want to write in its place. Then we will use our magnetic fields to rotate the bubble of interest around. Again, let's pretend he's this orange and red one, and we want to write that one. What we will do is we will swap it. So I will take the original orange and red one out, and I will take this blue one and swap him in its place. And then we can keep moving around. All 272 of these did this at the same time. So we loaded 272 bubbles. And then it can, keep going around with its rotating magnetic field. But now, we've got a different bubble in there. We've got this little blue one is in there. And if we wanted to, wanted to write the next sector, then we just advance it to the next one. Now let's say we want to replace, well, we've got to have our replacement lined up there. We will do a swap. We'll swap them out. Oops. We will swap that one into his place. And now we have replaced both of those. Again, we did this 272 times. And once again, the bubbles can merrily go around in their loop. What does this thing need to implement to do this? Well, it needs 272 loops. Each loop is going to have a replicator to replicate the bubbles for read, and each loop is going to have a swapper to swap the new bubbles in for write. So that's what the chip, that's what's implemented in there. So there will be a pair of pins for the replicator, and there'll be a set of pins for the swapper, and then there's some pins that run the there's some pins that run the rotating magnetic field and to move all the bubbles around, and it's really as simple as that. Okay, there's one more thing I want to talk about, and that is these hex numbers printed on the top. These are known as the boot loop. So as I've mentioned, this device contains a number of loops that are read in and out for data, but it also contains a fair amount of spare loops because during the manufacturing process some of the loops are going to be bad in it. So what they do is they put a map here on the top of the chip that lists which loops are bad. Just looking at this, my assumption, just based on how the bits are set, is probably that a bit is set to 1 if a loop is good and set to 0 if a loop is bad. Now this data is also encoded into a special loop on the chip called the boot loop. So when you first boot your bubble memory module up, it will read the boot loop, get this map of which loops are good or bad, and that tells it which loops to send and receive data from inside the chip.
That takes you into a couple of very useful publications. So this first one is by Intel Magnetics. It is a Bubble Memory Design Handbook. And this has in it sort of an overview. You can see how the parts work together, and data sheets on each part. So you've got a little bit of a data sheet here on the 1 megabit bubble memory. So this is the the actual the sort of the big metal chip looking thing, the 7110, where the magnetic bubbles and the substrate are at. So if you look in here, it shows you these are the parts that you need to get in order to make yourself a bubble memory system. You need the bubble memory module, the 7110. You need some drive transistors. You need a pre-driver, which drives the drive transistors, a current pulse generator, and a formatter and sense app. Now, those are all of the parts that are immediately associated with the bubble memory. To move the bubbles around, to read the bubbles, to write new, to swap in new bubbles, all of that's in there. And then, but you've got this 7220 bubble memory controller. And this is where you get into something that you can easily interface with a microprocessor, because it'll have a standard data bus and such. So you scroll down here, there's a picture of the bubble memory module. This is the one that fits on the chip carrier, the one that's kind of like a leadless package, snaps into a socket. But if you go down and you look at the 7220 bubble memory controller, if you want to implement one of these, this is where you'll look to understand how to talk to the thing, because it's got pretty much a normal data bus. Actually D0 through D8, it has a bit for parity. You don't need that. But, then your read and your write strobes, right there it is, chip select. So basically, you interface it like a typical I/O device. You give it a chip select and then a read or a write strobe. It can interrupt you when it wants you to do something. All that's described in there. And it has a series of registers. There is a FIFO, which holds the data that's going between the CPU and the bubble memory. That's your communication mechanism. But there's also some control registers. So you've got, like a status register, tells you the state of it. You've got command register. You can give it various commands. If you've implemented something like a floppy controller, then this all feels a lot like a floppy controller. You send a command to it, you kind of wait while the command is in wait status, and then your data comes back and you pull the data bits in, or the data bytes in, one at a time until you've read the entire sector. And so it really, whoever designed this 7220, they designed it to be, in my opinion, much like a floppy controller. So it's very easy to interface. Craig Andrews wrote a bunch of code. I leveraged that code for my H8 driver that interacts with this thing. And it's really straightforward code. It's easily readable and you can understand how it works. Your next best bet is to look at this application note 187. Now this has a lot of detailed information on building yourself a bubble memory board of your own. Now, some of it's a rehash of what we just looked at, but it'll actually talk about how to make bigger bubble memory systems, like an 8-wide system where you have 8 of these bubble memories, each sending their data. It's got a schematic for an entire 8-wide system in here, all broken out. It talks about the data transfer rates. So much like a floppy controller, you do have to read the data relatively quickly. You can't just screw around. The data is coming off of this thing. You better be about reading it. If you don't read it in time, you'll have a buffer overrun. It'll tell you how to lay this out. Some of this is very important, like there's some sense wires here for pickups from the 7110, from the magnetic bubble pickups into the sense amplifier that it wants. It wants you to put pretty serious ground planes around that to isolate those traces, prevent noise from getting into them. It really just, again, it spells out everything you need to do to make one of these. And if you look at the various implementations that you find manufacturers have built, they go ahead and they build this thing kind of, exactly the way the manual here says to build it.
Okay, here's an SBX 251 bubble memory module. Hold it up here so you can get a good angle on it. This bubble memory module that goes with a multi-bus, multi-module card. Now, multi-bus, you could buy something called a multi-module card, which was designed for multiple of these smaller modules to plug into. It's kind of a piggyback connector. You plug it into your multi-module card. Maybe you've got a couple holes up here that would secure it down with screws, I would think. And then you could plug the multi-module card into your multi-bus chassis. That's kind of how that would work. I've never done anything multi-bus. This is the only piece of multi-bus gear that I own. You can find these things on eBay, ranging sometimes as low as $50, sometimes around a couple $100. You can find ridiculous priced ones at like $400. I wouldn't spend that much. It's way too much. You might have to look around to get a deal on one of these. The nice thing about this is it implements the reference circuit all on one board. You've got the memory module here, the bubble memory. If you look at it here, make sure we got a good angle. If you look at it here, this is an Intel branded one. It's got the Intel lettering there in the traditional Intel blue. Other ones you will find will have MTech branding on them. Just depends on what vintage of module you get. There are two different size modules. This here is the through-hole one, so it's got pins come right out the back of it and mount to the back there. You can see a redundant set of pads here, which would be for the socket version. So the socket version was a little bit older. It's got 4 holes here to mount the socket, I'm assuming. Redundant set of pads for the socket, you put the socket on. And then your bubble module is kind of a leadless thing that plugged into that socket in some way. At some point they decided it would be cheaper or simpler just to mount the modules to the boards. This here is slightly newer than the older ones. This board must have been designed to accommodate either. But you've got all the traditional circuits here that go with the bubble memory reference implementation, the 7220 controller, the two 7254 drivers. Here is probably the 7250, the 7230, the 7242, a couple silver mica filtering caps, a resistor pack. Like I say, all of this stuff is just directly right out of the reference schematic. You've got the oscillator there, the clock divider, 75463 used in the power fail stuff. It does have this connector back here. The documentation for this is well documented on the web. We could get the pin out for that and use this in something if we wanted to. Now, the advantage to buying one of these, you don't have to build up the board yourself. Somebody's already done it, and it's already even an industrial board. This is probably a 4-layer board because I don't see a ground plane on either side. And the reference manual really says use ground planes, especially around this coil sense stuff over here. So it's probably a good quality board if you wanted something in this form factor, you wanted to interface it to something. Be a good starting point to find one of these on eBay and tinker around with it, which is probably what I'll do with this one. Now another option if you want to get into bubble memory is one of these MTech bubble memory kits. I got this one here from Craig Andrews, and if you open it up, it's got almost everything you need. It doesn't include the 7220 controller, but it includes all of the other chips, the 7254s, the 7250, the 7230, and the 7242. And then it's got a memory module. Now the memory modules, some of them different generations. This here is a MTech one. So what happened was Intel either spun off or sold the magnetics division. So you'll find some of the newer ones are branded MTech. But anyway, you have almost everything you need here. This is the through-hole version of the memory module, ready to mount right onto your circuit board or into your SIP headers, whatever you want to do. Little baggie here with the hardware to fasten it down. Then you'll need to get the bubble memory controller. Also purchase some of those from Craig. I've got one of those right here. You'll need that one too. Buy that one separately. And then you've got enough to build yourself a bubble memory board if you want.
Okay, now let's talk about the schematics for the bubble memory board that I'm going to show off with my H8. So here it is. It's actually just 2 pages. The first page has the H8 interface stuff. So over here I've got the H8 bus. It's a 50-pin bus. I've actually got it replicated 3 times for different particular pinouts. You may have seen that with my other H8 boards. Off of that bus comes I/O read, I/O write, memory read, memory write. We don't need the MEMR and MW, but we do need the I/O read and I/O write. I buffer those through some 74 HCT 14s. This actually, I copied all of this off of one of my other boards. That's why it's got MEM, W, MR. And up here we have a 74 HCT 540, which buffers our data lines. Now I should mention, if you're not familiar with the Heathkit H8, it uses inverted signals for all of its lines. So it's actually inverted address lines, and then this 540, it inverts them again, which kind of like de-inverts them, puts them back the right way. We've got a bidirectional 74 HCT 640 or 74 LS 640. I've had better luck with the LS and the HCT part. It's the same thing for the data bus. You know, it takes the inverted ones, puts them back to normal, and this is actually bidirectional. So depending on whether you're reading or writing, you'll flip that one way or the other. Then I used an ATF 22V10 or a GAL 22V10, a programmable logic device. I use the same one. A lot of my boards, and it implements the address decode. So it takes your 8 address bits, I/O read and your I/O write, and it generates the strobes, to talk to the 7220 bubble memory controller, as well as to flip the direction on this and to drive a couple of LEDs. I probably could have used a smaller PLD. You could have even got by with something like a 74 HCT 688, just compared the address lines. There's no magic in this thing. It's a little bit overkill. We need power for this board, and the bubble memory is going to take both 12 volt and 5 volt. And a beefy amount of it. It's kind of no joke there. It's going to take 400 milliamps on the 12 volt and, maybe about the same on the 5 volt. So a couple of footprints for a 7805 and a 7812. You can also use switching regulators. I like using the Pololu switching boards instead of the linear regulators. The standard footprints for those, lots of signal conditioning around them. I also copied something that Craig had in his board, which was a DC-DC converter. So you can take the 5 volt and step it up to 12. We're right close to the limit on the H8, what it can supply for 12 volts. So it has an 18 volt line, which we will step down to 12. Supposedly that's only good to about 500 milliamps. And, we're going to take like 400 milliamps of it to run this bubble board. We're running an H8 with an 8080 board that's also requiring 12 volts. Or you had a DRAM board that needed 12 volt, or you had the serial board that needed 12 volt, easily start overtaxing the HA's 18 volt line there. So, it's possible this boost converter here to step up the 5 to 12, that could be something one might need to explore. So I use the same part that Craig did in his SB85 board. Down here to the actual guts of the thing. Now this is a great implementation of the bubble memory design book, the book I presented earlier, straight implementation of what's in there. I mean, it's like part for part. The schematic, I actually copied it from Craig's SBC85 board. He added a few things, like he added this MCP130 as a reset detector to improve the power fail circuit. I think he might have done a few other tweaks around the power fail, but it's really, if you read the design handbook for bubble memory, you'll understand everything there is to know about this. I really don't need to go in and try to explain this circuit because it's already explained in that literature. The one thing I do want to harp on a little bit is the power fail. Now, you don't want this thing to run out of power when it's writing the bubble memory and fail in the middle of a transaction. You could end up with data loss because you remember what I showed you before, those bubbles, you're circulating them around. If you glitch this thing out while you're flipping bubbles around in the loop, you could corrupt the data. So you've got a couple of decent beefy capacitors. I put them down here as 470 microfarad. Actually, on mine, on the 5 volt, I upped it to 1,000 microfarads. But like I say, a couple beefy capacitors. You've got, filtering capacitors, 15 microfarad, 47 microfarad, 0.1 microfarad, 1 microfarad, just scattered all over this thing. Have super clean power drive capability. And then you have a power fail circuit and a reset circuit, which goes to the extreme to find out, hey, is the system powering down? Is that voltage dropping below 5 volts? The MCP130 is a nice modern way to do that, but also inside of these other circuits, they are looking and watching as well. But it looks, has that dropped? And if so, you send a power fail signal to these chips, and they complete those bubble memory transactions with that remaining power before the power goes out and the data gets corrupted. So very important that the power fail circuit works. Very important that you meet the 5 volt slew rate that is in the guidebook, and very important that you have lots of filtering and lots of spare capacity in your 5 volt. So when I tried this out, I actually did put this on the oscilloscope, and I looked at the 5 volt to make sure that the 5 volt was meeting the spec in the Intel design handbook that said that signal needs to meet in order to be compliant with that power off. And that's really all there is to it. So it's really just the interface glue and then this here thing right out of the bubble memory handbook.
Okay, here is the completed H8 bubble memory board. So the big chip is, of course, the 7110AZ bubble memory, and all of the bubbles are in there. Surrounding it are all of the support chips. So you've got the two 7254 drivers, the 7250 pre-driver, the 7230 and the 7242, and the 7220 bubble memory controller. It has its own clock down here, an 8 megahertz clock divided by this 74 HCT 74. Over here we have the H8 bus connector, with its bus transceivers, the 540 on the address lines and the 640 on the data lines. We've got the 74 HCT14 that I use to buffer the I/O read and write, and the GAL 22V10D that I implemented the address decoding logic. Lots of capacitors around, so this is the large 1000 microfarad 5 volt and the 470 microfarad 12 volt. The red ones are all 15 microfarad, and these other black ones I believe are 33 microfarad, which happened to be what I had at the time. Up here we have the 5 volt regulator. I use a small Pololu switching regulator, as well as the 12 volt regulator, which is a 7812 because I don't have any switching regulators. I mounted it to a heatsink. You can see how I did that here. It's just a small aluminum heatsink that I happen to have. Let's look at the back of the board. Not a whole lot to see here, but you can see there are some mounting screws here for the bubble memory, the 7110AZ. It really doesn't need those, but in an industrial application you probably would want to mount it securely because it is kind of a heavy component with a lot of mass. You can see, you may be able to notice there are no backplanes visible on this. This is because this is a 4-layer board. The bubble memory guidebook really recommended 4-layer boards, so I decided to go with that, and it's a little bit simpler to lay out a 4-layer board and get it right than it is to lay out a 2-layer board and get it right, because you can just take the 2 inner planes and dedicate them to power, and it's a simple way to have good power going everywhere. So let's go ahead and try this thing out next. Okay, let's go ahead and install the bubble board. So right now I've got my H8 configured with an 8085 CPU board. I've got my compact flash back here, my H17 floppy controller, and my terminal and vinculum board back there. And we're going to take the bubble board and plug it into this slot right here. And now it's time to fire it up. Okay, let's go ahead and turn it on. We can see the computer's active. Got the 2 power lights on the bubble board for the 12 and the 5 volt back there. You should be able to see them lit up. And I'm going to hit 044, which will boot my compact flash. Compact flash boots very fast. There we go. And we've got this this bubble tool, which was written by Craig, and I ported it over to the Heathkit H8 HDOS. So if we run bubble board tool, and we can do some various things with this. So for example, there is a test mode. I'll push T for test, and it'll go through and it'll test all the pages. Now it'll print out an error if it runs into an issue. It does take it a while to go through all 2048 pages, so we'll just reset and go do some other things. Let's go back in here, 044 again. Okay, so the bubble tool, it allows us to do several things. So for example, we could read some memory. Let's hit R. We'll read from page 0 on the bubble, and let's put it at 4000 hex in memory, read 1000 bytes, and let's dump 4000 hex. Again, this is memory. We'll go to 4400. And this is what the test put in there before. It just wrote some consecutive numbers to the various pages. Now I have some test data in RAM. Let's try writing that. So first let's look at the test data. Let's do 5100 to 5200. And I stuck the opening lyrics to Star Trek there. So what we will do, this time we will write. Let's write it to bubble address 0. We will do memory address 5100. And let's do 0100 bytes. So we wrote to the bubble memory. Now let's do a read from the bubble memory. This time we'll read again with page 0, and we'll read it to 4000 hex and read the whole thing, and then dump 4000 and 4100. And there, that is what we read back from the bubble memory, which was the Star Trek lyrics like I put in there. So the bubble memory, it's working great. This diagnostic tool that Craig wrote and I ported to HDOS was really useful in making sure that the board is working properly. Now, I also wrote a disk driver that would allow me to use the bubble memory as a disk device. That was my original intent with this. And I already had a RAM disk driver that I used with my 8 megabyte board. I probably featured that in a previous video. So I took that RAM disk driver and I repurposed it. You know, I gutted the RAM disk portions. I put in the bubble memory portions instead. And now we have the ability to use bubble drives on the H8. So if I do an init, I'm going to tell it to initialize disk BD0. And remove the disk, hit return when ready. Hit return when ready. And there's a bunch of junk sitting in there, which is actually the test pattern written by that test command. So yes, initialize the disk. And let's tell it 600 bubble trouble. Why not? Now you see here we've got some debug info. My driver actually has the ability to output debugging messages, so that allows you to kind of see the transfers that are going back and forth to the disk. So we did a write at block 0 of 900 hex bytes. That was the initial stuff from init. Now it's asking for a list of bad sectors, hit return, and now it's initializing parts of the disk. So now we have an initialized disk. Let's see, we're done here. No more. I'm actually going to turn off debugging, BD : no debug, because all the messages are kind of annoying. Let's do a reboot 044. That will take in those new driver settings. And now we should have, on BD0, the bubble disk should be initialized. Yeah, bubble trouble, there it is. And it's empty. So what I'm going to do next is I'm going to do sysgen. We'll just do sysgen BD0. Whoops. BD0. There we go. And this will transfer the operating system to the bubble disk. So you can see lots of stuff is going on there with reads and writes on the bubble. The reads are actually because it's checking the status bits. You know, every time it writes, it has to check and see if there's a room in the FIFO. So you actually see a lot of blinking on the read LED, even when we're not actually reading data, even when we're just writing data. For some reason, I always get that same error whenever I do a sysgen, that it has trouble copying something. Now if we do a dir BD0, there's all kinds of stuff. These are all the drivers that were sitting there on my on my compact flash. So I'm actually going to take, I want to rename one of them. So whenever you do a sysgen, it actually swaps devices because it wants everything to be SY0. So it took the old SY0 and it has renamed it to BD, which that confuses me. So BD0 : it's actually HA. BD equals 0 : BD.BBD. So we'll fix that. And then I also want to do a pip. I want to do a BD0 : equals from the compact flash basic .abs. We'll copy the basic interpreter over. Now we've still got 142 free sectors, so we've used a little bit over half the disk. It's only a 128 kilobyte disk, it's not huge. But let's go ahead, we should be ready to boot from it now. So I'm going to power off the computer. I'm going to yank out
my compact flash board. You know, we don't need any compact flash anymore. And then we'll power the computer back on. Okay, let's go ahead and boot. I'm going to hit 090. So you see there we've got bubble. It's recognized bubble. Wants me to hit the space. That's because it's freshly sysgened. Hit the space. And we've got our boot prompt. So we'll go ahead and boot from it. And now we are running exclusively off of our bubble drive. So, you know, my compact flash board is just sitting down here, unused. We do a dir here. And we have, just before we have our 202 sectors, we can run basic. There we go. And that completes the demo of the bubble memory board.
Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff. Bye.